Our population globally is growing, and our urban population is also growing rapidly, and so we need to find ways to build cities more sustainably for growing populations.
In the next 30 years, about 150 major cities in the world will double in terms of their urban population. What is going to happen will be really a residential need that will be almost catastrophic in scale unless we find a new way of building.
Architects can no longer ignore the responsibility they have towards choosing more eco-friendly materials or sustainable materials. What we are trying to do is we're trying to show that it is indeed possible to build structures that are architecturally interesting using natural materials.
So Oakwood Timber Towers began as a first project as we were invited by Cambridge University and Smith & Woolwork engineers. They were interested in a tower of about 100 meters for study, but when we were discussing as a group, we thought, why not just simply go to the maximum, which is 300 meters.
Building with wood, engineered wood at the scale of skyscrapers, is the first time we've had a new large-scale structural building material in over 150 years since structural steel and reinforced concrete. We know that global carbon emissions need to come down, and building with wood is an excellent alternative to building with steel or concrete.
What we're really beginning to find, though, is that it's a new method of construction that really has the opportunity to change the industry and bring us into the 21st century, unlike any other material.
CLT is an abbreviation for cross-laminated timber. It's wood glued, so they're 90-degree different. Glued together, you get very large panels that architects and engineers currently use more or less like slabs of concrete. There are lots of advantages to using cross-laminated timber. Among them, it sequesters carbon from the forest. It is an engineered material, so it's the same every time you ask for it. It's usually cut and pre-manufactured in a factory, so it comes to site ready to assemble. It's very light, particularly compared to steel and concrete, so you can get taller buildings on the same sized foundations. And we hear a lot about the change that would be possible to global carbon emissions if all people became vegetarian. I think we can make an argument that cities ought to be vegetarian. When we talk about timber buildings, the three most common questions are fire, forests, and rotting. Wood is combustible and it will burn, but the type of wood that we're using in these very large-scale skyscrapers is different. So these solid wood panels they behave much more like trunks of trees. So as the wood burns, the charcoal is very insulating, so it protects the unburned wood underneath. The goal is that if you remove the source of heat, the fire will go out. The Center for Natural Material Innovation at Cambridge University is located in the architecture department. It's funded by the Leverhulme Trust, and it brings together biochemists, plant scientists, architects, engineers, chemists, and mathematicians to try and find ways to use plant materials at a larger scale in the built environment.
So I'm Paul Dupre. I'm in the Department of Biochemistry in the University of Cambridge, and I work on the structure of wood. Well, there are several reasons why wood is so strong. There are three main parts to wood: the cellulose, xylan, and lignin, and it's not been understood how they stick together to make this remarkable material. And the shape of the xylan molecule, it has evolved, we presume, to be precisely complementary to the surface of the cellulose fibers. So when they come close to each other, they're able to zip up like two parts of a zip, and that brings the whole molecular structure together and makes it remarkably strong. And we might be able to use that knowledge to improve the properties of wood, perhaps by finding components that we can put in the wood to preserve it or change its structural properties.
When you build a tall building, you have to be very conscious of how they will respond to lateral wind loading on the side, because they Even though they're big, stiff, huge structures, they will still flex about to some extent in the wind. One of the challenges with timber buildings is that a skyscraper built out of timber really will be lighter than it would have been in concrete or steel. And that means that they are more susceptible to moving around in the wind, to vibrating, which could make occupants uncomfortable. So we need to mitigate this and understand how to design appropriately in timber versus in other materials.
Most failures lie in connections. Could be either for concrete buildings or even for timber buildings. So we need to make sure that we provide safe, reliable and robust connections in any case. And this is where research is needed, especially when we need to address higher limits, for example in tall buildings. So the different colors, it's a visualization of the magnitude of the stresses. Usually red color indicates higher stresses, usually at the lowest levels of the building, whereas blue can indicate smaller stresses.
We work on small molecule compounds that can penetrate into the extremely tiny pores inside of large timber. We are all made up of extremely small polymers and even smaller molecules, right? Our DNA, our proteins. And so you can say that we can engage and interact on the human scale, but of course what's happening are many processes at a much, much tinier scale. And in the same way, the buildings of the future may be held together through rapid interactions that are happening at the molecular level, but having a macroscopic effect on the human scale. And perhaps in the future, we'll be able to completely remove the concept of a nail or a screw holding two timber joints together. Perhaps they can all be done through small molecules that come together at very specific interfaces and give the wood unbelievable strength.
We have to ensure that wooden buildings of the future, even wooden buildings today, are made from sustainably managed forests. Deforestation is a big problem in forests around the world, but it is usually a result of cutting forests for agriculture rather than cutting forests for building materials. The sustainable forests, which are not subject to deforestation, are planted as crops. In Europe, in the last few decades, the sustainable harvest has grown by an area the size of Portugal. The amount that can be harvested, that hasn't actually been harvested. So the forests are larger by a tremendous amount.
There's a new science called biophilia, and incorporating timber into cities will improve the sense of nature returning to human habitations, to cities particularly. So there's a very strong connection psychologically. Our heart rates are reduced, we're less stressed, which is something you want in a city center. We become more sociable, therefore, apparently. So we see enormous benefits in using the material.
So I can imagine a future where we're growing our buildings, where we live in a building that's been made from a tree that was cut down not too far away, and when that tree was cut down, two were planted in its place. From the first skyscraper in 1885, it was less than 50 years that we got to the 381 meters of the Empire State Building. In the near future, we will see taller and taller wooden buildings, and it will be common for us to accept them, and that we will see some wooden skyscrapers on the skyline of London, New York, other great cities in the world.
The group's research on timber towers not only pushes the limits of architectural design, structural engineering and scientific research, but it also synthesizes them. We hope to solve a host of problems that can trickle down to other building typologies by showing that the very limit of engineering can be achieved using timber as a natural material.